Okay, in this video we're going to look at what we do when we have a function of x on the right hand side of our differential equation. So this is now a non-homogeneous differential equation because we have a term which doesn't contain any y or y derivatives. So what we've looked at in previous videos is when the left hand side is equal to 0, and we've looked at the auxiliary equation and how we can solve that. We now consider cases when we have a general function on the right. So to solve such a differential equation, we actually split this up into two pieces. So I'm going to say the general solution, which I'm going to depict as y subscript gs. That's a general solution of my differential equation, which I might end up writing as just y. That's going to be equal to the sum of two pieces, so ycf and ypi. Now ycf is the complementary function of the differential equation, and that is essentially the solution, the general solution to the differential equation if f of x was 0. So what will happen when you run this part of the solution through the left-hand side is that will always equal 0, so it doesn't contribute anything to the right-hand side. The good thing about the complementary function is that contains both of the arbitrary constants that we need for the general solution to the second order differential equation. The particular integral, this is a particular function of x, which when you run it through the left-hand side of the differential equation will always equal f of x. And adding them together takes advantage of this linear property of differentiation. So when you differentiate y, you differentiate that and you differentiate that separately, and the same with the second derivative. So when you run the sum of these two functions through, then this will kick out the 0, this will kick out the f, and when you add them together, you end up with f. Okay, so that's the idea of this method. And we're going to have a look at how we find a particular integral now. Essentially, the particular integral all depends on what f looks like. So if f is a constant, then the particular integral will be a constant. If f is a linear function, then we try a linear function. If it's a trigonometric function, we would try a trigonometric function, and so on and so forth. Let's have a look at a table where we can start to get a feel of what these particular integral functions are going to look like. And I've called it a trial PI because sometimes these particular integrals won't work. And we'll have a look at how we deal with those a bit later. So if f of x is a constant, a given number in the question, then our trial PI, which I'm going to call ypi, that is going to equal just some number. Now what I do with this is I take this definition and I run it through the left-hand side of my differential equation. In this case, obviously the first and second derivatives will both be 0. And then that will allow me to find a numerical value for alpha, which depends on the numerical values of a and c. Oh, actually, maybe I shouldn't have put a there because a was used up there. Maybe I should call that d. Okay, if it's a linear function, again, maybe I shouldn't have called it a and b, but these a's and b's are different to these a's and b's. A linear function, which might be a linear and a constant term, or it might just be a linear term, then my particular integral will be a linear function. So that would look like alpha x plus beta. And if I take this definition and run it through the differential equation, then I will have a pair of simultaneous equations in alpha and beta to solve. There'll be a numerical answer for alpha and a numerical answer for beta. And that will give me my particular integral. Okay. Just note that even if there isn't a b on the f of x side, I still need to include a beta on my particular integral side. And the reason for that is because if I differentiate this, then I'll end up with a constant. So I need to deal with that constant. So I include the constant in the first place. And similarly, I can extend that further to a quadratic case. So ax squared plus bx plus c, again, different a's, b's and c's to the top. But ax squared plus bx plus c. B and or c could be 0. And the important point is this is a quadratic polynomial. Then my particular integral would be just a general quadratic. So alpha x squared plus beta x plus gamma and I would run this through my differential equation up here to get numerical numbers for alpha, beta, and gamma. Okay, and of course I could apply that to any polynomial. Whatever the highest power of x is here, that is the polynomial I need to include over here. Okay. Three other types of functions then. We've got the exponential function, so a number for a, again, different a number for a and a number for k. Then the particular integral we're going to try here is going to be an exponential function which looks the same, so e to the kx, e to the kx. Okay, so the k goes through. So if the function was e to the 2x, then I would be trying e to the 2x. The number out the front here doesn't have any impact on alpha directly. I need to run this through my differential equation to get a numerical value for alpha. Okay, I'm looking for alpha, but k I've extracted straight from f. Trigonometry, the particular integral, I've got a and b and a no number k as well. So I would need to try alpha times the cosine of kx plus beta times the sine of kx. And I'd have to include both cosines and sines, even if one of those isn't there, again, for the same reason as the linear case above, because when I differentiate the cosine and put it through the differential equation, I'll get sines. So I need to deal with those sines, okay, and vice versa. All right, so yeah, include both if you've got a trig case. And also, again, similar to the exponential case, the contents will go through. So if this was e to the 5x, sorry, cos of 5x, then this would be cos 5x sine 5x. And a hyperbolic case, which could come up as well, I guess, exactly the same as the trig case above, except it's the hyperbolic functions rather than the trigonometric functions. Plus beta times sine of kx. Okay. And if your f of x is any combination of these, so say maybe it's a constant plus an exponential, then I would have an alpha plus a beta e to the kx. And I'll just start combining these together. Okay, so that's the general theory of how we get to the particular integral form, at least. Let's see this in action. So let's find the general solution to some differential equations. So we're going to start with the complementary function. So I'm going to write CF on the left-hand side of my page. And to get the complementary function, I'll pretend that this is the homogeneous case. So in this case, the 10 is actually a 0. I'm going to follow the theory taught in previous videos. So lambda squared plus lambda minus 6 is 0. So I'm going to get lambda plus 3, lambda minus 2 is 0. So that's going to give me lambda values of minus 3 and positive 2. From there, I can state my complementary function, which I'm going to call yCF. And that is going to be equal to ae to the minus 3x plus be to the 2x. Okay, that's my complementary function. All right, and now for my particular integral. So I'm looking at my f of x now, and I'm seeing that this is a constant. Therefore, my particular integral trial, ypi, will be a constant. I'm going to call alpha. I need the first and second derivatives to put into my differential equation. So ypi primed is 0, and in this case, that just happens to be the same as my second derivative as well. So if I now take these three definitions and run them through the differential equation, I will get minus 6 alpha equals 10, which gives me my numerical value of minus 5/3 for alpha. That then is my particular integral, because the particular integral was just alpha. Okay, therefore ypi equals minus 5/3. Right, and now the final step. I've got my complementary function, I've got my particular integral, and then I can state the general solution. So therefore, y is going to be equal to the complementary function, which is ae to the minus 3x plus be to the 2x plus my particular integral, which in this case is minus 5/3. And that is the general solution of this differential equation. Okay, let's try another one. Complementary function. So we're going to jump straight to the auxiliary equation, which in this case will be lambda squared plus 2 lambda plus 2. It's going to be equal to 0. Pretend that f of x is 0 to get my complementary function. And then the solutions to this auxiliary equation, well, we're going to have lambda is equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a, which in this case is minus 1 plus or minus I. So I've got a pair of complex conjugates. So my my complementary function this time, ycf, that can be written as e to the minus x, okay, so e to the real part times x, into a times the cosine of the imaginary part times x, plus b times the sine of the imaginary part times x. That theory is all covered in previous videos. If you missed that, then do check it out. Okay, particular integral time. So for my particular integral, this is an exponential. In this case, a was 2 and k was 1. Okay, but it's the one that's interesting. That'll always be an alpha at the front. So the one I'm going to try, ypi, is going to be an alpha e to the x. Okay, if this was a 2x, that would be a 2x. If it was a 4x, that would be a 4x. Okay, it's the exponential bit that comes through, and then the bit at the front is what I'm trying to find. Okay, how much of this do I need? Y primed of pi is the same thing, alpha e to the x, and y double primed is also the same thing, alpha e to the x. Okay, take these three definitions and run them through the left-hand side of my differential equation, and that's going to give me alpha e to the x plus 2 times y prime, which is 2 alpha e to the x, and then I've got plus 2 times y, which is going to be plus 2 times alpha e to the x, and I want that to equal, always equal, 2e to the x. Notice that all the e to the x's will cancel, and I'm left with 5 alpha equals 2, so I'll get the numerical value that alpha is 2/5. Now I've got alpha is 2/5, plug it back into the particular integral up the top, so I get ypi is therefore equal to 2/5 e to the x. All right, almost there now. The general solution is the sum of the complementary function and the particular integral. So therefore y is going to be e to the minus x into a times the cosine of x plus b times the sine of x plus 2/5 e to the x. That is the general solution of this differential equation. All right, one final example before we close up this video. Ooh. Here we go. Okay, so same process again. The complementary function, we're going to jump to the auxiliary equation. So we've got 2 lambda squared. Just be careful because it's now acts as a function of t, not y as a function of x. Okay, so just make sure you're paying attention to the variables. So 2 lambda squared minus 3 lambda minus 2 is equal to 0. So we're going to get 2 lambda and lambda is equal to 0, and then that must be a 2 and a 1, and I want -4, so it's going to look like that, which gives me my 2 lambda values of -0.5 and 2. So that means my complementary function, ycf, is ae to the minus, I didn't pay attention to my variables, did I? xcf is ae to the negative t on 2, okay, it's the -0.5 from the lambda, plus be to the 2t. Okay, particular integral. So I'm looking at the right-hand side here. I've got e to the 2t. So I'm going to be trying x, particular integral, is going to be equal to alpha e to the 2t. The first derivative then, pi dot, is 2 alpha e to the 2t. And then xpi double dot is 4 alpha e to the 2t. All right, take these three definitions and run them through the differential equation. That's going to give me 8 alpha e to the 2t, because I've got 2 of my second derivative, minus 3 of my first derivative, so it's going to be minus 6 alpha e to the 2t, and then I've got minus 2 of my function, that's 2e to the 2t, and I want this to be identical to e to the 2t. Okay, all right, simplify the left-hand side. That's going to give me 0, because I've got 8 minus 6 minus 2, so it's none of those. Oh, there's an alpha in there as well. Is identical to e to the 2t. Hold on, that is an issue. There's a contradiction there. Okay, 0 can never always be equal to e to the 2t, so that is a problem. This is a case where our particular integral has failed. Okay, so let's explore why this particular integral has failed. So this failed because our trial particular integral was part of the complementary function. So if we look back at the complementary function that we obtained, we had ae to the negative t on 2 plus be to the 2t. There we can see we've already got something times e to the 2t as part of our complementary function, which means that when you run that through the left-hand side, it's going to equal 0, which means this was always going to fail. Okay. So we cannot use, I've got the x's and y's rather than t's and x's, but okay. So we cannot use this as a particular integral. When this happens, what you do is you take your particular integral and you multiply it by your independent variable and you check it again. Okay, so in this case, we need to take our particular integral and times it by t, and then we're going to run it again. Okay, so this one failed, but now we're going to try it with the next one up. So we're going to try xpi is equal to alpha t e to the 2t. Okay, so if ever it's going to fail, then you should times it by t and run it again. And you don't have to run it when you know it's going to fail. You can see it's going to fail because it's already part of our complementary function. So we know it's going to fail. So you don't have to go through all of this algebra. We can just jump straight to, oh, that's not going to work. Let's try this instead. If this fails, this will work. If this will work, this won't work. Okay, this only works if this one doesn't. Okay. Okay. So let's run this one instead. So we've got a product now, so we're going to have to use the product rule. So xpi dot is going to be equal to, let's pull out the alpha, and we're going to get the t times the differential of e to the 2t, so that's 2t, plus e to the 2t times the differential of t, which is 1, times e to the 2t. Okay, so there's our first derivative. And then the second derivative, xpi double dot, again I can pull out the alpha. This time the differential of this, that's going to give me 4t plus 2. And then I've also got plus this times the differential of this. The differential of that is 2. So it's going to go there. So I can pull out the 4. So I get 4 alpha into t plus 1 e to the 2t. Okay, so there's my function that I'm trying, my first and second derivatives. So if I take these three definitions and run them through this differential equation, the coefficients of t should actually cancel to give me nothing, and then I'll be left with just functions of e to the t. So I want 2 times the second derivative, so 2 times this, so I'm going to get 8 alpha into t plus 1 times e to the 2t. And then I want minus 3 times the first derivative, so minus 3 times this, so that's minus 3 alpha into 2t plus 1 e to the 2t. And then I also want minus 2 times my function, so minus 2 times this one up here. So minus 2 alpha t e to the 2t. And I want this to be equal to e to the 2t. I want this to be equal to the right-hand side. Okay, so I'm going to get, I'm going to first of all divide by all the e to the 2t, they can all disappear. So I'm going to get 8 alpha t minus 6 alpha t minus 2 alpha t. Okay, so that's all the ones where the t is present. And now look at the ones where the t is not present. I'm going to get plus 8 alpha minus 3 alpha. And I want that to be identical to the number 1. We can see that this does indeed cancel. So 8 minus 6 minus 2 is 0. That's actually what I had up here, wasn't it? 8 minus 6 minus 2. So that disappears. And I'm left with this. So I get 5 alpha is 1. Therefore, alpha must be a fifth. Now I've got alpha as a fifth. I can take that and put it back into here to give me my particular integral. So xpi is a fifth times t e to the 2t. This particular integral now works. If I take this and run it through this left-hand side, it will always be e to the 2t. Okay, and now I've got our complementary function and a particular integral. I can now state my general solution. So therefore, y is equal to x is equal to a e to the minus t on 2 plus b e to the 2t plus a fifth t e to the 2t. And because the e to the 2t there is common amongst both of those terms, I could then actually condense them and say x is ae to the minus t on 2 plus b plus t on 5 e to the 2t. But this line is fine. Either of those is good. Okay, so in my next video, I'm going to have a look at some more examples. Again, some of those particular integrals will fail, and we'll have a look at kind of seeing them work out in those questions. So check that out. And thank you very much for watching. If you've got any questions, please just drop them in the comments below.